A screen recording on how to use Desmos to find the derivative. Uh, and this is the case where we are just going to do an estimate using our definitions. So I have put in the equation of the bungee jumper that was in our textbook, and now I'm going to adjust the window so it's got a little bit better picture of what we want to do here. So the bungee jumper, the x-axis should start at 0 and then go to something like, I think, 20 seconds it had for the bungee jumper. And now we got something that looks a little bit better. The bungee jumper, I zoomed out, but let's just move it down. Jumped from about 200 feet, went down, then back up and down, and eventually it settled at about 100 foot. So they had about a 100-foot bungee cord on this bungee jump. So this is the equation that models it. Now the definition of the limit was basically the slope. We got a definition of the derivative, I should say, is a limit function, and it was the limit of f of b minus f of a, all of that. So I got to put this in parentheses. Over b minus a. Now what it's asking me here is, do I want to put something in for the b and the a? So let's say I was trying to find the slope at 2. Now let's see if we can get this to disappear here. 2 is about here, so I'm looking for the slope right about there. That's close to the point, but I want the slope. And so I'm going to put a as 2. So if I make a slider for a, I can move it to 2. Okay? And then I'm going to make a slider for b, and I'm going to try to get b closer to a. And you notice that up here, it's calculating the slope. Now I want to get it really close to 2, so I'm going to change my scaling here to be from 1.9 to 2.1, stepping by thousands. Now with that, so if I press enter, I can now slide this and I can get it really close to 2. 2, it's undefined because I'd be dividing by 0, but if I go to 1.999, I get negative 51.105. If I go to 201, I get 51.08. So it's about negative 51. And the height was in feet, so the change in the height was feet, and the change in A and B, that was the time. So I'm getting the change in feet over the change in time, or negative 51 feet per second is how fast it's negative, because they're falling, how fast they're falling. Now I could have done this at, say, maybe wonder what it was at 5 seconds. So I could have changed A to 5, and then I could have done B, then would have to get closer to 5, so I'd have to change this to be 4.9 to 5.1, and then return, and I can get it really close to 5. And it looks like at 5 it was positive, so it's going up 21.8 feet per second. So I'm finding the slope at those places. The other equation for the instantaneous velocity, the derivative, the slope, the is a limit, and I'm doing the limit here by getting as b approaches a. So I made a be 5, and I'm making b get closer and closer to that same point. That's the limit part that I don't show here. The other definition of the derivative is f of a plus h minus f of a over, so I got to go back and put a parenthesis and parenthesis over h. And we want to know when this gets close to 0. Now this is more convenient for figuring it out at two different places. There's an a here, but it's using the same a as I had here. So if I want to know at 2, I would go back here and put this on 2. I could have just gone up here and typed it. And I need a slider, and I want h to get close to 0. The other one was as h gets close to 0. So I want this to go from negative 0.1 to positive 0.1 and return. And now if I get this really close to 0, I'm getting that same slope that I had before, negative 51.08 or negative 51.10. But yes, slope at 2 is whatever. Now, if I wanted to get close to 5, h has still got to go to the 0, so I don't have to mess with this one anymore. I just put 5, and oh, there's a slope close to 5. And what if I want to know it at 10? I could just go here, 10, and now it's got the slope at 10. Let's look at the graph. At 10, it's got a negative slope. It's falling at about 10.45 feet per second. Okay, so that's how you do it on Desmos. Now I'm going to do another video doing it on a TI calculator. Okay, so in this video,